I'm Dev Nag. I'm the CTO and co-founder of Wavefront. We do enterprise metrics. Our customers include Microsoft, Workday, Box, Intuit, Groupon, Lyft, Okta, many of the top SaaS companies in the world. And so I'll share what I've actually learned from these guys, how they actually structure their operations, how they use the product, and especially how they use smart alerts. I'll divide and talk into three parts. I'll first of all talk about how smart alerts really reduce to metric anomalies. In the second section, I'll talk about how to think about anomalies, a framework for approaching anomalies in this pipeline. And third part, I'll talk about the future of operational anomalies, all the cool stuff we see coming down the pike in the next 3 to 5 years. So what characterizes alerts that are not so smart, right? Well, they kind of have a very simple way of looking at the world. They have thresholds that divide good from bad. They tend to work on univariate data. They look at one data series at a time. And they tend to have all or nothing severity, right? Either something's firing or it's not. And the problems that this causes is that it causes a lot of noise. There's a lot of false positives and a lot of false negatives. And this actually means that you can't use relationships between different data sets. You can't use, for example, a ratio of one metric against another. And all this causes essentially too many people getting involved in every issue. So you have too many ops people, too many developers getting involved in these issues. It's very expensive for companies. And so that's kind of the core problem at the heart of alerting, right? There's not a good fit between the sort of solution and the problem space with modern cloud architectures. So a smart alert would have, hopefully, these things fixed, right? It would have a more expressive language for defining what anomalies actually are. It would allow you to express actual relations between different data sets, not just the univariate data. And finally, you have a way to do targeted escalation, right? Be able to get the right alert to the right team at the right time. One of the most interesting operational design patterns we see is this idea that people don't scale up their ops teams anymore. They scale out to the dev teams instead. All our biggest customers do this. There's just too much complexity to have a team of 10 or 20 or 30 ops people handle the whole system. And so when they do this, they actually have something interesting as well that goes along with that. They actually take all of the developers and have them write their own alerts. They self-serve analytics, right? Because they know their code so well. They instrument the code, they deploy it themselves without any kind of interference from ops, and they watch that code running in live all the time. And so they have a lot of information alerts, right? They're firing all the time. They're not even really alerts, they're more like notifications, just to give a sense of how the behavior of the code actually is on production for their one silo of the system. Now, that information, the big blue circle, is way too much for the ops teams, right? They don't want to see all that stuff. That's a curiosity for them. They don't have the luxury of time for that, right? All they care about is severe paging stuff that happens right now, right? Something they have to fix, something that's actually actionable, right? But there's a trade-off here, because the bigger you make that blue circle of information alerts, the smaller the red circle is, right? The more the developers understand how their code runs in production, the more you actually head off these problems before they become true operational issues. So we see a spectrum here across developers doing more informational alerts, watching their code on production almost like a remote profiler or debugger, and operations looking at things that are actually problems right now. But to do this, you need a couple of things. You need information, data from all across your stack and very deep as well. You also need a very powerful language to express anomalies that go far beyond thresholds, which brings us to metrics anomalies. So what is an anomaly? If you look at the dictionary, anomalies are defined as something that deviates from what is standard, normal, or expected, right? It's something that's not expected, something that's unusual, right? Not good or bad necessarily, just different. Now, why do we care about anomalies? Because anomalies really tell us sometimes when to act, right? We touch production systems for two reasons. One is to change or upgrade functionality in a planned manner. The other is to fix something in an unplanned manner. Anomalies help us with that second path, right? Now, why metrics as opposed to events? Events are what you see in logs. Events are occurrences, something happened. A user logged in, a web page was requested, right? These are all events. Occurrences that have timestamps, they have arbitrary annotations, right? It's actually totally fine to have duplicate events. Here we have at the bottom an example of 4 event lines. The second and third are completely identical, exact same date timestamp, exact same event type, same username. Some guy pushed the button twice to log in. There's 2 events here. Any logging system will store those separately, right? It's 2 different events. So the metaphor for events is really a list. It's a list of things that are weakly connected or unconnected. Metrics are not occurrences. A metric is actually a measurement. They have timestamps, and they have annotations. So they kind of look like events, but they're not. In metrics, you're taking a measurement, and if you measure the same thing at the same time, you should get one value, which means you should not have duplicates. Duplicates are redundant. So the metaphor for metrics is actually a function that maps time to value, right? To numerical values. Events don't need numerical values at all. The logins at the bottom of the events example didn't have numbers at all, right? It was just logins and times. Now, why is this function metaphor so powerful? There's 3 big reasons. The first reason is that we have a whole bunch of mathematical machinery we can bring to bear on top of these functions. The second big reason is that we can actually columnize or vectorize this data. We can take all of the values for a given function, pull them out as a big vector, compress them together, store them as a giant blob. You can store tens of thousands of points or more in one blob, which means it's far cheaper to store. You can pull that data back out so much more quickly than with events. And finally, you can leverage human intuition, visual intuition, at scale with functions, which I'll show you in the rest of the talk. So how should you think about anomalies? Go back to definitions. Anomaly is the complement of normal. There's 2 ways to define anomalies. One is to define the anomaly directly and say, here's a mathematical function that says this is an anomaly. The other way is to define what normal is and say everything else is the anomaly. In practice, the second way happens to be easier. I'll show you 10 examples with a shared theme, a secret theme, if you will. The first example of an anomaly is the easiest. Thresholds, ranges, right? The blue line sort of goes between 3 and 10. It spikes up. That's the anomaly, right? The red box has the anomaly in all these charts. It's pretty obvious, right? This is the baseline. How about in this data? The red box has some anomaly. What is the anomaly there, right? It doesn't jump out at you. If I actually highlight one of these lines, you can see, okay, I see one of these lines kind of has a baseline that's pretty static, pretty stable. It jumps up for an hour and a half, comes back down. That's the anomaly. But in the previous chart, you can't see that, right? You can't see it when it's hidden with 100 or 1,000 or 10,000 other lines. It disappears into the noise, right? However, there's lots of ways to fix that, right? You can take a standard deviation or an interquartile range. We have a whole bunch of techniques to say how unusual is each new point of each series compared to its own recent history, right? If you typically live in this neighborhood of values and you jump way outside or way below that, we can show that to you. And now you can see that the outliers stick out. There's 3 of them, right? And they're very obvious to see. You can see exactly when they start, when they end. And everything else has been scaled down to 0. So here, normal is defined as a small window deviation, right? How about here? This is a very volatile kind of chart here across 2.5 weeks. It goes up and down. Why is that one crevice the anomaly? Why not something else on there? Well, because even though this looks very jagged and random, if you take a seasonal ratio, you divide each point by the point exactly 1 week earlier, right? Week over week. You see the ratio is always between 1 and 1.1. It's very, very stable. But then we have that one dip down to 0.75, right? That's the anomaly. And again, it's hard to see. This doesn't stick out at you, this does, right? What's the anomaly here? I see 2 parallel lines, right? There's no structure here whatsoever. Here, we're going to take a rate. These are counters, right? If we take the rate, all of a sudden the structure is obvious. Blue line actually jumped up for a second. The orange line dips down for a couple of days before it comes back up, right? But you can't see that in the previous data. It's all hidden away, right? And here it becomes obvious, right? You take a rate, the structure is clear. So normal here is a constant rate. Here we have a serial pipeline. A lot of our customers have this. They have a pipeline of data. Data goes through the pipeline. They have throughput rates at each stage of the pipeline. And you can see the pink line at the bottom is the output, the final stage of throughput, right? And it drops way down. And the rest actually drive up, right? We have a stall in the pipeline. Points are getting dropped or getting delayed for some reason. And so here, for example, the anomaly is the divergence, right, of the top and the bottom of this chart. And you can actually take a max, subtract them in, and see what that should be, right? The anomaly is very obvious to see here. This is essentially the net stall through the pipeline, right? So here the group range is normal. It should be low. When it gets higher, that is the anomaly. This is a similar example where you have a parallel balancer, a load balancer, for example. And you don't just care about the max versus the min. You care about the spread across all the different channels, because you know when you have a big spread, you tend to have too much utilization on the top and not enough on the bottom, it costs you money on both sides to handle that, or performance. And so here we could do a variance, or a square root of a variance, which is standard deviation, right? And here you can see they spike up at that event, right? That's the anomaly right there, where those two kind of bumps are. And so here, normal is a low group variance. When the group variance gets too high, that is the anomaly. However, let's say a different team on the same company, looking at the same hardware, at the same chart says, there's no anomaly here. Because they're downstream of this whole process, right? They don't care about the internals. They see total throughput. They take the sum of all these things. And they say, the sum is totally fine the whole time, guys. That's your problem. That's not my problem, right? Anomalies are in the eye of the beholder. They are subjective. They're not mathematical truth. We use math, we use the language of math to express them. But we encode our own intuitions about what actually is happening here, right? That's our domain knowledge. That can't be replaced. It's all about your perspective. Here again, we have a very, very jagged chart, right? And that red box has the one anomaly. And again, why is that the one anomaly, right? It's not the highest value. There's the value at the right that's higher than the red box. What's going on here? Well, here we're looking at CPU, right? This is a resource metric, right? Let's say we also show a demand metric, like requests per second. And you can see those two metrics tend to go together 5 days a week, right? The week before, the week after, they're very, very close together. But then that one Saturday, the request stays low and CPU goes high. So now the anomaly is actually the relationship between these two metrics, right? Not one metric by itself. If you take a simple ratio, you can see, okay, the ratio tells you when there's an anomaly, right? A low ratio means it's expected. This really high ratio means it's unexpected. This is kind of the opposite case, right? On the left side of the screen here, we have the blue and the green. They're sort of like going in very different ways, don't seem to have much of a connection. But during the anomaly, all of a sudden they seem inversely correlated, right? Perfectly inversely correlated. When blue goes up, green goes down, and vice versa. What's going on here? This is actually a very common pattern. This happens when you have two resources in blue and green that have a shared resource in red. It could be CPU, it could be storage, it could be a third service, it could be anything. Typically, they have their own behavior based on their own incoming requests, and everything's great. It's all copacetic. But all of a sudden, that third shared resource gets pegged. It gets saturated. And now those blue and green clients are fighting a zero-sum game on that shared resource. When one gets capacity, the other one loses it, right? And so you see this telltale inverse correlation. And you can actually do a moving correlation and show it, right? The correlation is typically between minus 0.5 and 0.5 around 0. But when you have this shared resource get saturated, it drops to almost -1. Very obvious to see, right? This one is pretty obvious by itself, right? Here we have missing data. We expect the data to come in at a regular frequency, and all of a sudden we have this gap of data, right? Every customer has had this problem at some point or another. And you can simply apply a moving count, which is like a moving average, just count the number of points reported in a given window, and say when the 20-minute count drops below 18 or 15 or 12, whatever, that is the anomaly, right? So here, a consistent reporting frequency is normal. And now you can take actually any Boolean combination or functional composition of any of these functions that I've shown you so far, put them all together. These are some actual alerts. We have customers that have alerts that are pages long because they have such a complicated definition of what normal is for their system. So I showed you these 10 or 11 types of anomalies, right? But I promised you a shared theme, a secret theme here, right? And the secret is that not all of these are equal. One is actually foundational, much more important than the others. And that one is actually the first one, the range. What I actually did in all those examples is I took a behavioral difference, extreme behavior, and transformed it using math into extreme value. Let me go back and show you. Here, for example, right, this is not an extreme value. It's not the highest value or the lowest value in this chart. However, when we do the deviations, all of a sudden, it does become the extreme value, right? We transformed extreme behavior into extreme value. Here, again, not extreme value. Extreme behavior becomes extreme value. Extreme behavior, extreme value. Extreme behavior, extreme value. Extreme behavior, extreme value. no extreme behavior by someone else's definition, and no extreme value, right? Extreme behavior, extreme value, extreme behavior, extreme value, and so forth. And the question is, why do we do it this way? Why do we have range or values elevate to this sort of lofty position, right? It's actually not about math. It's not about software. It's about us. It's about psychology. If I show you a bunch of almost identical entities, and I ask you, which one jumps out at you? You're all looking at the same penguin. It's the biggest penguin, right? In fact, in the owl picture, all the owls are looking at the biggest owl. Because we're so attuned to positional outliers, things that are taller or shorter or separated from the herd. We don't have that kind of instinct for other types of behaviors. If I show you this chart and I ask you which series of these 50 is reporting the least frequently, the data is up there for all of you guys to see, but no one here can do that. Unless Rain Man is sitting in row number 3 here, right? No one can do that. I'll finish by talking about the future of operational anomalies. Where do I see this whole industry going? One of the most obvious things that we're going to do is take all these metrics. We have people who've sent us millions of different metrics. I mean different metric names. Each of those metrics can have thousands or millions of points, right? Well, not all those millions of metrics are the same in importance, right? Some are far more important than others. They're KPIs. They lead directly to user experience, right? If you could pluck out the top 100 or 500 or 1,000 KPIs, we can do much more computationally expensive stuff in there, right? Deep learning, recurrent neural networks. We could actually build causal graphs between the different metrics here and show you what to expect, what to predict here in a much better way. A lot of metrics platforms allow you to actually annotate the data with events. They're not metrics, but they explain away metrics. Things like we just did a code deploy here, or we had a marketing campaign happen during this window of time. But the most important event is the operational intervention, right? It's the actions you took after an event happens to fix it. You failed over a load balancer, you replaced the database node, whatever it happens to be, right? If you put those event annotations into a system, right? All of a sudden we have both the input and the output to predict what the action will be next time, right? If we see enough of how you act, we can start to watch data in real time and say, hey, right now we see a 95% chance of no action, right? That's hopefully the common state. But every now and then we'll say, hey, we think in 5 minutes you're going to fail over. And you're like, what are you talking about? Nothing's happening here, right? And all of a sudden you see what the machine data saw, right? Well, we're skipping over the anomaly, over the alert, straight to the action here, right? We call this action labeling. The last trend is probably the most interesting. So you probably read this about a month and a half ago. Google used DeepMind, their deep learning subsidiary, to actually cut their data center cost by 40%, right? Huge, huge financial savings at the scale of Google, right? Now, what's cool is not that they use machine learning. What's cool is the kind of machine learning they used. If you think about machine learning, there's sort of 3 big approaches. There's supervised learning and unsupervised learning and reinforcement learning. In supervised learning, you have essentially inputs and outputs. You're trying to find the function that maps inputs to outputs, right? You might have images, and you're trying to find what's the name of the thing inside the image, right? In unsupervised learning, you have essentially just a stream of input, right? You're trying to find hidden structure inside that stream to figure out how to understand it better. Reinforcement learning is very, very different. In reinforcement learning, you actually have an agent that takes actions in some abstract computational context and gets rewards, telling it how well it's doing. And the rewards are not tied one-to-one with the actions. That's what makes it so hard, right? For example, I could be inside a maze, right? And I make a left move instead of a right move at one point, and 47 moves later, I escape the maze and get one giant reward. And I have to figure out how to assign credit back to my moves to understand which move got me here, right? It wasn't the one that just happened. It was something 47 moves back, right? A very hard problem. Almost all the cool stuff you read about, machines playing Atari games at human level, AlphaGo beating the world champion Lee Sedol at Go, have reinforcement learning at the core. It's a very generic way of looking at this machine learning problem. But the cool thing is, this all applies to our problem as well, to operations, right? We have a system, that's our abstract computational context. We have observables, these KPIs and metrics that come out of there in real time. And we have actions we can take, right? Our actions are operational actions. There are things like failing over and replacing nodes and changing memory configurations. The controller could work with a fitness function or utility function or reward function that takes all the KPIs and metrics and defines what you're trying to optimize here based on your own corporate preferences. Maybe you want to balance cost versus customer experience in one way on a certain day and differently on a different day. And the software would figure out how to take the right actions to optimize that function for you. And obviously, if it didn't work out, it would escalate, to someone else. But just like Google, you would start with a small system, a small subsystem, make sure it works, maybe on staging, gradually grow up to the whole production data center. And you would have something that would basically learn the system behavior better than any human could, because it could see all the information, all the data, and take the right action. I think the other two trends are really means to an end. I think this trend, this is the end. I'll finish by showing you some of what I talked about in action here with Wavefront. So I talked about vectorizing or columnizing data, right? This has huge performance implications. Let me show that in action, right? So this is a year of data between November of 2014, November of 2015. We have two different series here. This is actually CPU load, as you can see from the metric name here. Each of these is reporting once a minute. A year has about 500,000 minutes, so there's actually 1 million points being pulled off a disk and brought here to be displayed, right? Now I can take an average here. This actually takes the average at every single minute across that year, 500,000 times. It takes about a second. Now you might say, okay, I've seen year-long metric charts, like that's not really as special, right? What's interesting here? Well, if you look at the values here, it goes from 1 to 2 up to about 4 or 5, right? Very kind of low-key, mellow, undramatic chart. This chart is lying to you. It's hiding something from you. This is actually real data. We had an incident that you can't see on this chart. If you look at other systems, what they tend to do is summarize their data, or what they call roll up their data. After 8 days, they'll take the raw data and create hourly averages or daily averages. And assume, okay, the stuff that happened a year ago, you don't want anymore. We disagree. We keep all the data forever. We have one customer that sends us 250,000 points per second and has for years. They've sent us more than 10 trillion data points. We have every single one of those 10 trillion data points at full resolution. And you might ask, who cares? Why? Why is that important? I'll show you why. Here, we summarize data too, but we do it at the query time. We have all the data stored away, right? So if we want to change how we're looking at data, all we do is change our query. And we can see these outliers. If I change the summarize here, going from the average of each time window to the max, the anomaly jumps out at you. The CPU load didn't go from 1 to 5. It spiked to 90. 90. And came back down, right? But that 90 got averaged away during summarization, right? Let's go see how long that had to last. If I zoom in on this right here. The spike to 90 lasted from 435 to 442. It lasted 7 minutes. But you can see a 7-minute spike in a year-long chart in 1 second. My next example comes from a company that we worked for about 3 years as well. Giant SaaS company. They have 12 data centers around the world that all send data into Wavefront. This is one of their data centers. This is actually the switches inside one data center. These are all megabits per second. There's about 520 switches here, 520 lines. Between about 11 and 12 on this one day, the middle third of this chart, they had a massive outage, massive degradation. Customers complaining, SLAs violated, all kinds of bad stuff. And they wanted to figure out, how do I find what causes, right? How do I make sure it doesn't happen again? And they did what anyone would do. They did brute force search all over different metrics, trying to figure out what's going on. And one network engineer happened to find a single switch that had gone from a baseline of 2 megabits per second up to 10 megabits, and then back down to 2 at the exact same time that the outage began and ended at 11 and 12, right? This is like a smoking gun. This is like a funny shaped needle that he found, right? And he wanted to find all the other needles in that haystack of 520 switches that matched the needle he had found. How is he going to do that? They actually emailed us and said, is there a way to call your API and get back an image every 5 seconds? We'll have 2 guys writing it down, the ones that kind of match by shape. We're like, we love you guys, but that's a stupid idea. Don't do that. The right way to do this is actually take that haystack of 520 switches and correlate it against that one funny shaped needle. If I do the correlation, you get the answer in 1 second. You're searching by shape, by behavior, right? Not just by identity. All in real time. Now the customer obviously was thrilled to have this. They could figure out what was shared between these switches that acted funny. Were they all from the same vendor? Did they have the same firmware? All in the same service pool? And they could make sure that didn't happen again. But we asked ourselves afterwards, what if we hadn't found that first switch, right? That first smoking gun. We kind of got lucky, right? That was our hint to the whole puzzle. What if we didn't have that? Well, all you have to do is create a fake needle. A needle that is non-zero during the outage and zero outside the outage window, right? And now you can play the exact same trick. I can correlate that haystack of 520 switches against the window, not the needle. And if I do that, I get back the same set. So it works if you have a shape, and it works if you don't have a shape. That's all I had. Any questions? Yes, yeah, we're purely a cloud service. Yeah.
What's the pricing model and what's the collection agent? Do you have to install an agent on our bill?
Yeah, we actually give people a proxy, which is open source, just a little Java thing that listens for the graphite format, because that's such a common metrics format, and then basically it forwards it up to the cloud, to the Wavefront cloud. So usually it's a push model. You send data to us. We have a bunch of ways to have you collect your data, like CollectD will like work with us out of the box and so forth.
But network features can use SNMP?
Yeah, so people actually do use CollectD with the SNMP plugin to interrogate like network routers and that kind of stuff and send it into Wavefront.
And what's the pricing model?
We'll have actually our sales specialist talk to you, for sure, yeah.
Are there one or two industries that use your service a lot, and what do they particularly need?
So I'd say, yeah, SaaS is the biggest. If you look at our customer list, it's like heavily SaaS-based. I think because they have the most uptime sensitivity. They have like, actual dollars on the line. I think for people who are like doing kind of content or help desk stuff, like that's not such a huge issue. For SaaS, like they spend all of their time, ops and developer time, trying to fix like their cloud issues. The developers get pulled off in ops way too much, so we're helping to solve that problem. So I'd say like SaaS and IoT are our biggest two sectors. Yeah, we're actually like very open. So we have a portal that's actually based in the cluster itself for like these kind of web visualizations. We also have a full API. You can actually grab any queries results as JSON. So we have like a native R integration, Python integration if you want to use like pandas or SciPy or NumPy. We have a lot of data scientists who like to use us as sort of like a super fast backend that kind of scales forever. Yeah, so I didn't mention this, but actually everything you saw me do, all the functionality is completely available within alerting as well. You can create super complex alerts based on these functions and then have them fire like on our side. We'll actually call out to PagerDuty or email or do webhook call back to you.
How do you establish trust with the customer base?
So it's usually like they have something in place right now. They might have like something simple like Nagios, or they have something like OpenTCP or InfluxDB. So they have usually understanding of like kind of what kind of data they want. The trust part is about reliability. We have 4 nines of uptime, so we're super reliable. So we usually have a POC to show them like, we're super reliable. You can change your shape of data and have a lot of dynamism, and we'll stay up.
I guess I meant more like the 2ASL, virtual private network.
Yeah, we actually use VPCs. So each of our big customers has their own VPC, complete data isolation, process isolation. We offer SAML SSO, so we have a bunch of Okta and OneLogin customers. And Okta obviously is a customer of ours as well, so.
I understood that basically you have to define what's normal for the,
right.
for the environment. So are these finding out these anomalies basically are calculations against the baseline? When I think normal, I think just basically the baseline.
Mm-hmm.
But so these are calculations against the baseline and the anomalies?
So there's different ways. Baseline is like a very hard term to define. It's not a constant value. For example, if you have a counter that's like baseline is actually rising at a certain rate, right? And actually it gets much more complicated than that. So baseline is actually what the function is trying to define for you, right? And all the transformations that bring it down to this visual range, that's actually making the baseline static essentially, right? Which is why the outliers look like spikes up or dips down. So yeah, baseline is basically the same as normal for us.
Okay.
And if you have like, really simple data, like, expect it to kind of be in a certain range, like that's easy with any system. It's the hard stuff where we do so well.
Okay.
I put gigabytes of data from, I don't know, another system,
Mhm.
like graphite or something.
Yeah.
Can I load it all into
Yeah.
your system?
Yeah, so that's a common use case.
Is it possible to extract gigabytes out of your system?
It is. The hard part is actually reading it out of the old system, not writing it to us, because we can handle millions of points per second ingest. We can actually elastically scale our systems up and down because we have these VPCs that are dedicated to one customer. So we can take your cluster, expand it massively for the ingest, and then have all the data and then shrink it back down for your normal rate. We do that all the time. But yeah, a lot of customers want their historical data as well. So
Most of this data is just requests or events like that associated.
no, so actually, I would say like most of it is actually application data. So like the system data itself doesn't. Good.
So is it also that data correlating to the system?
It is, yeah. So usually people start with system data, exactly right. So like usually have like, hardware and CPU load, memory usage, network traffic, that kind of stuff is the baseline. And then the developers get involved. And we have hundreds of developers at a lot of these big companies that use Wavefront. And they're the ones who actually massively increase sort of the footprint of traffic. And they use the system level data to understand these correlations and like, what's actually affecting me right now. Am I causing a problem or is it like a hardware issue or something like that? But yeah, it's usually hybrid.
That's kind of the benchmark metrics.
Yeah.
Your app metrics are kind of weighted.
Yeah, if you look at like, the system metrics, like that's pretty consistent across different companies. Everyone has CPU load memory, right? Collect these like namespace is pretty standard. The application metrics is where things get really complicated. And so that's where like you have this sort of scale out to all the devs and they know what their metrics are called. They're not called anything that's like global, right? So yeah, that's the fun part.
Is all the server side? You do any of this client side? Like if you're serving a web app? JavaScript?
Do you mean embedding a chart? Is that what you're talking about?
Yeah, reporting metrics from the browser.
Oh yeah, so we don't actually collect the data itself, but we do have customers who collect the data from the browser interactions for UX type monitoring and send that into Wavefront. But they're the ones who collect in the first place and send it to their server first, and then it goes to us. Another common pattern that we see is that a lot of our customers have like huge message queues, like usually Kafka, and they take all the data across all the developers and front end, back end, everything all together. They put in that one giant pipe first, and then they basically push it out to Wavefront afterwards.
Which steps have you taken to make the service redundant in case you have an outage?
Yeah, so we're actually across a bunch of different AZs. We have at least 4 copies of every single data point. So we have actually 40 trillion data points for that one customer instead of 10 trillion. And we have essentially 0 downtime upgrades and failover because each side of the cluster can handle the full query and ingest power, which makes it very easy to like do these elastic expansions and contracts. You just do one side and turn off the other side and so forth. So yeah, we have, I have a whole architecture speech that I do for customers that's usually about an hour long. So yeah, I'll get to that eventually if we do business. Okay, well, thank you so much, guys.